All right, so now what we're going to do in section 8.1, we're almost at the end of the course. We have this section and then we have one more section afterwards, but we are now going to extend our applications for trig to situations involving non-right triangles. I mean, right triangles are the ideal situation. However, obviously many things come up in the real world that don't involve right triangles. So what I'm going to do is I'm going to derive the law of sines for you, not because you're responsible for deriving the law of sines, but so that you know where it actually comes from, okay? As with every other thing that we've done in this course, you don't have to memorize these formulas. You just need to know when and how to apply them. All right, so let's suppose we're given some non-right triangle. Okay, so I'm randomly going to draw a triangle. And I'm going to suppose this is angle alpha, this is angle beta, this is angle gamma. Opposite of angle alpha, we'll have the letter A. Opposite of angle beta, we have little b. And opposite of gamma, we'll have little c. All right. Well, as it stands, we're not really sure how to do this. So what we do is we always ask ourselves, well, when we're in a new situation, what do we do in a similar yet different one? What I'm going to do is I'm going to draw an altitude H. I'm going to draw it from my angle gamma. Notice you can draw a perpendicular line down from any one of these angles, okay? But we're going to drop the altitude so that we form two right triangles. Then we know what to do, okay? So I claim here that if I'm looking at my angle alpha, the sine of alpha is h over b. And I claim that the sine of beta is h over a, opposite over hypotenuse. Well, I can rewrite each of these guys in terms of h. I can multiply my first one through by b, my second one through by a. And I get h is equal to b times the sine of alpha. H is equal to a times the sine of beta. But h is h. It's the same thing. In other words, b times the sine of alpha is the same as a times the sine of beta. And we can divide both sides by a times b. And that gives me sine of alpha over a equals the sine of beta over b. Now, again, I could have drawn my, my line down from angle alpha. And if I did that, that would have given me sine of beta over b is equal to the sine of gamma over c. This, my friends, is your law of sines. Notice you take the sine of an angle over the side opposite of it is equal to the sine of this angle divided by the sine opposite, or the sine of this angle divided by the length of the side opposite, etc. Okay. In order to use the law of sines, I mean, you'll know really quickly if you can't use the law of sines because you won't have the correct information. But essentially, in order to use this, in order to have enough information to solve this proportion, you need two angles and a corresponding side. Okay. In other words, you need angle, angle, side, angle, side, angle. And the biggest pain situation is side, side angle. Okay. I am just telling you that we call this one the ambiguous case. Okay. When you have angle, angle, side, angle, you're going to be able to solve this pretty fluidly, get one solution, and life is pretty good. We call side-side angle the ambiguous case because there can be 0 solutions, 1 solution, or potentially 2 solutions. So when you're in this situation, that's a way of saying, hey, you got more work ahead of you. Okay. So these are the scenarios in which we use our law of signs. Okay. I'm going to take us through a few examples using our law of signs. Have this in front of your face. Okay. So to use our law of signs, the first example that I'm going to do is pretend this is a decently drawn triangle, as with everything else. Suppose this is 70 degrees, this is 50 degrees, and this is length 10. Okay. First off, you totally have to have a calculator for this section, and you need your calculator in degree mode. I will say that right from the get-go. Okay. All right, so what we want to do is we want to solve for the unknown sides and angles of this triangle. Okay, so I'm just going to randomly call this angle A, this little a, and I'm going to call this little b. Okay, in other words, we need to find angle A, side A, and side B. Now, for me, what I would do is I would say, I know that the sum of the angles in a triangle are 180 degrees. So I could take 180 minus the 70 minus the 50, and I'm going to get A to be a 60-degree angle. Okay. Now, from there, what we can do is we can set up our law of signs. The sine of A, which we know is 60 over little a, is equal to the sine of 50 over its opposite side is equal to the sine of 70 over its opposite side. Okay, well, in order to do this, I can solve 2 proportions. I can look at those 2 and say, well, they're equal. And when you have 2 ratios set equal, you cross multiply. 10 times the sine of 60 degrees is A times the sine of 50 degrees. Just cross multiplied. Now I want to know what A is. So I'm going to divide both sides by the sine of 50 degrees. So I can take 10 times the sine of 60 degrees divided by the sine of 50 degrees. Now, I don't know what that is offhand, but certainly I can compute that. So 10 times the sine of 60, and then I'm going to divide that by the sine of 50 degrees. And so we get little a, I'm just going to go 2 decimal places, is 11.31. In a similar manner, I can find side B right here. Again, by setting these equal and cross multiplying, I get B times the sine of 50 is 10 times the sine of 70. Divide both sides by the sine of 50 degrees. And what I'm going to be solving for is 10 times the sine of 70 degrees. And then I'll divide that by the sine of 50. And I'm going to get B to be 12.27. All right, notice it makes sense with our answers, just in terms of the size of the angles. Notice that 50 degrees is the smallest angle. This is the shortest side. 70 degrees is the biggest angle. This is the longest side, and A is in the middle in terms of the degrees, and therefore it is in the middle in terms of length of the sides. So this is one really thrilling example of using our law of signs. Okay, so what I want us now to do, oh, first off, sorry about this. Notice this is angle, angle, side. So we were in one of our nice situations. The side angle is when you kind of want to put your antenna up and wonder if you might have more than one solution, or none for that matter. All right, I want to do a few more examples before we move then into our law of cosines. So my next example is I'm going to suppose that my angle alpha is 43 degrees, my angle gamma is 69 degrees, and my side B is equal to 20. I claim this is very much the same as to what we were just doing. Notice here the triangle isn't drawn for you. The information's just given. Now, in any of those situations, I always recommend that you draw a picture. So, never has to be drawn to scale. I'd certainly be a hypocrite if I thought it would be. So here's 43 degrees. We know alpha corresponds with my little side A. We'll say gamma is 69 degrees, and that corresponds with my side C. And we don't know this angle beta here, but we do know that B is 20. So notice our first example was angle, angle, side. Notice this example, what we have is angle, side, angle. Okay, well, first off, we can get our angle beta here because again, we know that the sum of the angles in a triangle add up to 180. So if I compute this, I'm going to get my angle beta to be 68 degrees. The other things we want to find are the length of side A and the length of side C. We're going to go through the exact same razzmatazz with our law of sines. I'm going to say that the sine of 43 degrees over little a is equal to the sine of 68 degrees over 20, which is the sine of 69 degrees over little c. And again, in much the same way, we can solve for side A by cross multiplying, and we can solve for C by cross multiplying. So if we do that again, I'm going to have 20 times the sine of 43 is A times the sine of 68. So to compute A, and I'll leave you to do that because it's a matter of pushing buttons on a calculator, you're taking 20 times the sine of 43 degrees divided by the sine of 68 degrees. And similarly, in order to solve for side C, we're going to have C times the sine of 68 degrees is 20 times the sine of 69 degrees. So C is 20 times the sine of 69 degrees divided by the sine of 68 degrees. And again, this is just a matter of pushing buttons on your calculator. All right. Couple more. The next example that I want to show you is we're given angle beta is 50 degrees. Little a is 105 and little b is 45. Okay, again, let's draw a picture. This is my angle alpha. I know my side A is 105. Let's just have this be my angle beta, which is 50 degrees. And I know that's 45. And then this is my angle gamma and my little side C. Notice here, if you even wanted to start using the law of sines, let's see what we're going to run into. I think you'll grant me we have that the sine of alpha over 105, let's fill in what we have, is equal to the sine of 50 over 45, which is the sine of gamma over C. Now, I can certainly find my angle alpha right now. Okay, I claim I'm kind of stuck finding anything here. Because if I was to look at this equivalence here and cross multiply, I've got two unknowns. And there's nothing that we would be able to solve at this point. Notice we are in the ambiguous case. We have side, side, angle. So turn on your antenna. There may be no solution. There might be one solution, or there might be two solutions. Let's just wait and see what we come up with here. Okay. Well, notice the first thing that we can make do with is cross multiplying here. I'm going to have 45 times the sine of alpha is equal to 105 times the sine of 50. Notice we want to know alpha. So I'm going to divide both sides by 45 first, and I'm going to have 105 times the sine of 50 degrees and divide that by 45. Okay, that's going to be some decimal number, but notice we want alpha. So how do we get to alpha? Well, what we're going to do is we're going to compute this. I'm going to take 105 times the sine of 50, and now I'll divide that by 45. And I'm getting a long decimal. It's about 1.787437, etc. Well, where is your sign positive? Notice your sign is positive in your first quadrant and your second quadrant. Now, already I've got my brain spinning here, okay? The sign is always between -1 and +1. Notice we're outside of our range. But suppose we hadn't noticed that, okay? Suppose, we were going along and we would know that in order to solve for alpha, we would need to take the inverse sine of both sides. We'll do it. Hit inverse sine of that answer, and you're going to get a domain error. Okay, again, because my sign is always between positive and -1. So when this happens, this is honestly the case I smile the most in. There is no solution. Okay, one more here. Let's do another angle side side. And how about for this one, I'm going to have my angle alpha be 43.1 degrees. I'm going to have my side A be 184.2. And I'm going to have my side B be 242.8. Okay, I claim that we're in a side-side angle scenario here again, but let's go through this. I've got 43.1 and this side is 184.2. Okay, this is beta, and I know that this is 242.8, and this is gamma, and that's little c. So again, let's plug what we have into our law of sines. I have the sine of 43.1 degrees over 184.2 is equal to the sine of beta over 242.8, which is equal to the sine of gamma over c. And just like in my previous case, I can't do anything here yet, because I'd first need to find this angle here, which will then give me that angle there, since the sum of the angles of a triangle add up to 180, and then we could find that side. So let's first hone in on what we can deal with. I can cross multiply here. I'm going to have 242.8 times the sine of 43.1 is equal to 184.2 times the sine of beta. I want to know beta ultimately, so I'm going to divide both sides by the number in front. I claim then I have the sine of beta is 242.8 times the sine of 43.1, and that's divided by 184.2. All right, let's see if we have better quote unquote luck this time. So I have 242.8 times the sine of 43.1. I'll divide that by 184.2. And what that's going to give me is the sine of beta is about 0.9006, sorry. And it keeps going. All right. Notice we're going to have a solution here. Notice I'm solving my trig equation that the sine is equal to some positive number. This allows for the fact that I could have two solutions because my sine is positive in my first and second quadrant, and that will total to be less than 180, right? We can't have angles in our third and fourth quadrant here because the sum of all the angles have to add up to 180 degrees, okay? So what I'm gonna do is I'm gonna hit in, oopsie, sorry about that. I'm gonna hit inverse sine of that value, and I claim I'm gonna get beta to be 64.24 degrees. That's one possible solution. This could also be my reference angle in my second quadrant. So I know that now we're going to have at least one solution. So the question is, are we going to have one solution or are we going to have two solutions? And I'm about to show you how to know. So one solution for sure is 64.24 degrees. Okay, and this might be the only one, in which case I'll get rid of that subscript. But another possibility is this 64.24 is my reference angle. So I'm going to take 180 minus 64.24, and I'm going to get 115.76 degrees. And I'm going to ask myself, is this possible? Well, how will we know if it's possible? We know that angle alpha is 43.1. So if I can take this angle and add it to my angle alpha and still stay beneath 180 degrees, I'm going to have another solution. Okay. If this angle plus this angle already goes over our sum total of 180, that's when you would say, nope, not a possibility. Okay. So we have two possible solutions here. So I'm going to have two possible values for my angle gamma, right? Because if this is 64.24 and I add that to my 43.1, I've accounted for 107.34 degrees. Well, take 180 minus that, and I claim that this angle gamma is going to be 72.66 degrees. Add these up, you'll get 180. On the other hand, my other solution, 115.76 plus 43.1, sure got me close, right, to 180 degrees, because this plus this add up to 158.86. But that allows for a really teeny tiny angle for gamma here. All right, so what do we still need to find? Well, notice we found our two angles. We have one more side to find. We need to find the little corresponding C1 and C2 in each of these scenarios. So to do that, I'm just going to keep I'm not going to use this middle ratio here. I'm just going to keep using this. You could put in each of these angle betas too, but all I need to find is my sine of, or my little C value. So I've got to use this last proportion. So my first scenario is to put in my one value for gamma and then find C1. And we can do that by cross multiplying. And then to find my other possible triangle solution, I can take the sine of alpha over A. Notice now I'm putting in my other possible angle to get my other little side C. So we can do this again, cross multiply. So I'm going to have 184.2 times the sine of 72.66 degrees. Just cross multiplying. And now I'm going to divide that by the sine of 43.1. And I'm going to get, in this case, my little side C is 257.33. Notice it makes sense that this is longer, this is a bigger angle. And finally, if I want to find my value of C2, notice this is a tiny angle, so this side is going to be really short. I'm going to have 184.2 times the sine of 21.14 degrees. And then I'll divide that by the sine of 43.1. And I get 97.23, which relatively speaking is much smaller. Woo! All right. There's our law of sines. Okay. Again, you use your law of sines when you have two angles and a corresponding side. In other words, one of those three situations. But I claim, what about if we know side, 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 or side, angle, side? If we have that information, the law of sines will not work. I mean, you can't have the sine of A over some number, I'll just say 5, equals the sine of B over 7 equals the sine of C over 9. Notice we have no way of solving this simply because we don't have enough information to solve any proportions. And I could show you similarly that it would mess up with side, angle, side as well. So guess what? We need a law of cosines. Now, I'm going to derive the law of cosines for you in much the same way as I did the law of sines. You're not responsible for the derivation. I just want to show you that this just does not come from midair. Okay, so bear with me through this. If you're overwhelmed by the derivation, fast forward and totally ignore me. Okay, so again, we have a non-right triangle. The derivation looks a little different, but this is alpha, this is A. I'll just have this beta B and gamma C. It doesn't really matter what we call each of those. And what I'm going to do is I'm going to drop my altitude H again. When in doubt, go back to what we know. And I'm just going to say that if this whole side is B, I'm going to call this portion of it X. And if the whole thing is B and this portion of it is X, I claim the length of this side is B minus X. Okay. So it's law of cosines. Let's use it. Okay. I claim that the cosine of alpha is adjacent over hypotenuse. In other words, I can rewrite X as C times the cosine of alpha. Okay. All righty. Well, now what I'm going to do is going to seem a little funky, but I'm going to hone in on this right triangle right here. Okay. I think you'd grant me that the length of this side squared plus the length of this side squared is equal to the length of my hypotenuse squared. I think you'd also grant me that we could do the same thing with this side, to get x squared plus h squared is equal to c squared. Okay, well, I'm going to solve each of these for h squared because h squared is h squared, no matter which way we look at it. So I'm going to isolate my h squared here and isolating my h squared over here. Now, if you wouldn't have thought to do this, don't sweat it, okay? Again, this is just like the icing on the cake, if you will. Well, if h squared is equal to this and h squared is equal to that, and we're in the same triangle, essentially then I can say that a squared minus b minus x squared is equal to c squared minus x squared. And now we get to do some algebra, okay? So I have a squared minus, I'm going to FOIL this out and then I'll distribute my negative sign. I get b squared minus 2bx plus x squared. I'll distribute my negative sign. I get a squared minus b squared plus 2bx. 2bx minus x squared is c squared minus x squared. Notice I have minus x squared on this side, minus x squared on this side. I could say, well, let's move this guy over. But if I add x squared to both sides, that's going to cancel. So I have a squared minus b squared plus 2bx is c squared. Well, x, notice, is c times the cosine of alpha. So what this tells me then, first I'm going to solve it for, say, a squared. A squared is b squared plus c squared minus 2bx. Let's just move everybody to this side. And now I'm going to plug this in. Minus 2b, but x is c times the cosine of alpha. Woo! So the length of one side squared is equal to the length of the other side squared plus the other side squared minus 2 times the lengths of each of these sides times the cosine of the angle opposite the side we're looking for. So there's 3 different ways to write this if you're solving for A versus B versus C, but you'll see the similarities, right? B squared is going to be A squared plus C squared minus 2AC times the cosine of beta, right? Alpha with A, beta with B. We could also say that C squared is A squared plus B squared minus 2AB times the cosine of gamma. Those are our laws of cosines. Okay. Now, I want you to note the consistency and with what we've already established. If one of our angles is 90 degrees, okay, we know the cosine of 90 degrees is 0. Okay. So if I do that, just let's do the bottom guy because it's the closest one to the bottom of the page. If I have, say that my angle gamma is 90 degrees, I have a squared plus b squared minus 2ab times the cosine of 90. But what is the cosine of 90? That's equal to 0. So notice, if I do have a right triangle, I'm simply left with my Pythagorean theorem. Isn't that super rad? So because of this, the law of cosines is oftentimes referred to as the generalized Pythagorean theorem. I mean, you have to admit that's pretty cute, okay? Again, follows exactly what we've known with right triangles. All right, so to wrap up this section, what I want to do is just a few more examples, but I'm going to be using my law of cosines. So for this next one, suppose this is 20. This is 60 degrees. And this is 28. Now, I know it's tempting to say, oh, 60 degrees is a common angle, but this is not an equilateral triangle. So let's just name our other angles, and we're just going to use our calculator to do this. Now, we do know the cosine of 60, of course. Okay. Well, what is it that we want to find? We want to find the length of this side. So I could say, using my law of cosines, that c squared is a squared, so 28 squared, plus 20 squared, minus 2 times 20 times 28 times the cosine of 60 degrees. Okay, this is one long calculator strand. I mean, literally, I would just be plugging this in. Sorry, the lighting isn't great, but literally I would be doing 28 squared plus 20 squared minus 2 times 20 times 28 times the cosine of 60. And that's going to give me that c squared is 624. So we're going to take the square root of that to get 24.98. All right. Now from here, I have all three sides. I could use my law of sines to find my angles alpha and beta, or my law of cosines. I'm going to use my law of cosines just because I want to show you something. Okay, so notice what we have left to find are our alpha and our beta. Okay, so what I want to do is this. If I want to find, I'm going to rewrite my law of cosines. Notice I want to find alpha. So this is the formula that I'm looking at. Notice I could rewrite this solving, isolating my cosine of alpha. Okay. How would I do that? Well, what I could do is scoot my b squared and c squared. And I'm going to show you that this is an alternative way of writing your law of cosines. And it's handy to have this. So first I just moved those two terms over. Now I want to get this alone. So I'm going to divide by negative 2bc. And I'm just going to write cosine of alpha on my right-hand side. Notice this negative, I'm going to just change the signs of these guys. That'll give me a positive b squared, a positive c squared, and a negative a squared over 2bc. So another way I can write my law of cosines, isolating each of them, is as follows. A squared plus c squared minus b squared over 2ac. It's handy to have this because now you have the law of cosines. If you want to find an angle, now you have them isolated. So how would we find the cosine of alpha, for example, here? Well, we know the cosine of alpha is equal to b squared, which is 20 squared, plus c squared. Oh, and we found c, which is 24.98 squared, minus a squared, divided by 2 times b times c. And in a similar manner, we can find beta. I'll do all my calculator work momentarily. I can find the cosine of beta is a squared, so that's 28 squared, plus c squared, and we found c to be 24.98 squared, minus b squared, over 2 times A times C. And so now it's a matter of doing these computations. Thank goodness for technology. So 20 squared plus 24.98 squared minus 28 squared. And then I'm going to divide that by this whole quantity. Remember, when you're dividing by a whole quantity, put the whole quantity in parentheses. Your calculator knows its order of operations. So I have the cosine of alpha. What I have for this mess is about 0.24. So then I'm going to hit inverse cosine of that angle, or of that value, sorry, and I'm going to get about 76.1 degrees. And we could actually just use the fact that the sum of the angles in a triangle adds up to 180. And if we already have that one angle is 60 degrees, we can easily get beta just by adding 76.1 to that, and then subtracting from 180. Or you could put all this in your calculator and then hit inverse cosine. But regardless, this is what you're going to get for B, or angle beta, excuse me. Woo! Okay, I know this is a long one. I'm gonna just do 2 more examples, and I think that should be good. Okay, suppose now, not drawn to scale, this is 13, this is 11, and this is 20. Okay, doesn't matter what we call each of our angles. I'm just going to note that we have side, side, side. And because we're looking for angles, what I would recommend you do is take these versions of your law of cosines and go from there. Okay, so for example, if I want to find my angle alpha, cosine of alpha is 13 squared plus 20 squared minus 11 squared over 2 times 13 times 20. And then I'm going to have to do the inverse cosine. Now, if you're wondering why aren't there a possibility of 2 solutions for these, notice we're going to be getting our cosine of alpha equals some positive number. And the only other quadrant that has positive values for cosine is our 4th quadrant. So it's already out of bounds. All right. And then similarly, I can find my angle beta. That's 13 squared plus 11 squared minus 20 squared divided by 2 times 13 times 11. All right, so I'm going to get these 2 just so that we can make sure that we're all on the same page. Don't forget to put parentheses around your denominator. I get about 0.86 here, so I'm going to hit my inverse cosine of that. And I'm going to get my angle alpha to be 30.51. I've got to do one more of these inverse cosines, okay? So now I'm going to do 13 squared plus 11 squared minus 20 squared. Divided, 1 second, beta, 13 squared plus 11 squared minus 20 squared, okay. And I'm going to divide that by 2 times 13 times 11. Okay, now the other reason why I want to do this is notice we get a 2nd quadrant angle. So I'm going to hit inverse cosine of that guy. So here I'm going to get beta to be about 112.62. I could do another cosine, law of cosines, but if I have 2 angles, I'm going to go with it. I'm going to take 112.62 plus 30.51. Add those together, subtract from 180, which is going to give me my third angle. I know it seems like a lot of work, and it is a lot of button pushing, but that is all it is button pushing. Okay, once you identify which trig function to use. Okay, one more example. I haven't done a word problem example, so I'm going to. Suppose this is an island, and we want to find the distance, or no, let's not say that's an island. Suppose this is a lake, okay? Suppose we want to find the distance across the lake, okay? So this is what we're looking for right here. Well, what a surveyor did is taken measurements as shown, okay? So a surveyor's on an island. They took a measurement and found that at this point where the surveyor's standing, they're 900 feet from this end of the lake. They're 800 feet from this end of the lake. And they can also measure that this is 70 degrees. So if they have this distance and they have this distance and the inner angle, notice we're in a side angle side situation. Because we're in a side angle side situation, we get to use our law of cosines. We want to find this side. So I'm going to say x squared is the length of one side squared plus the length of the other side squared minus 2 times the product of those lengths times the cosine of that angle in between. And because we really want to know what the distance across the lake is, I'll actually compute it. Again, this is now just a matter of pushing buttons on our calculator. So I'm going to get x squared to be a huge number. And so I'll take the square root of it. And I claim that the distance across the lake is about 978.515 feet. All right, I know that was a lot, but I wanted to be sure I went through a sufficient number of examples so that you would feel good about moving forward. Thank you.